Let's begin. You guys got a test or something? Well, that doesn't explain poor attendance today. It's quite a bit fewer people than we normally have, yeah?
Yes.
Although I guess people are slowly filtering in. At any rate, any questions? In that case, we'll begin. Right. So we are going to continue our dive into the types of numerical representations of numbers inside of computer systems. Although I suppose some people in the class feel they already know everything there is to know about numerical representations of computer systems and see fit to read books in class. Didn't even faze them. A little bit rude. Thank you. Especially when you're only in the third row. If you're going to read books in class, do it in the back row, please. Anyway, so let's talk about how floating point numbers are represented. Floating point numbers are, generally speaking, represented the same way you might expect decimal numbers to be represented. There is an error in this slide, incidentally. This is decimal. These 2's should be 10s. This is what I get for leaving things to TAs. So, in general, the way that the decimal system works is if you have the decimal point here, anything beyond the decimal point is multiplied by decreasing powers, well, increasing negative powers of whatever the base of the system is. So in this case, although these are 2's, you can see in the formula it's correct. We have 2 times 10 to the 1 plus 0 times 10 to the 0 plus 5 times 10 to the negative 1, negative 2, negative 3, the tenths, hundredths, thousandths, etc. It turns out that things are not plugged in. Come on. Give me strength. Please. There we go. All right. So, if we were to represent fractional numbers inside of the binary system, we would be doing so in almost precisely the same manner as we do in the decimal system, except the base is 2 now. So this is a representation generally known as fixed point arithmetic, although this name will not appear in the slides. Fixed point arithmetic is actually a thing that is actually used when you have fractional numbers that exist in very small environments like embedded systems design or hardware design, where you don't necessarily have the luxury of full float representations. So in general, in fixed point arithmetic, you have a set number of bits which precede the decimal point, although this is not the decimal system anymore, so the decimal point, although it's still called the decimal point, no longer represents decimal arithmetic, if that makes sense. We have fractional arithmetic, is a better way of talking about it. We have a fixed number of bits preceding the point, and we have a fixed number of bits coming after the point. This is a representation that's actually used. But one interesting corollary of this particular representation, the fractional components which we use to compose numbers in binary arithmetic must be inverse powers of 2. As such, we're talking about 1/2, 1/4, 1/8, 1/16. All of those lovely fractions which you come to know and love if you've ever tried to build anything with a measuring tape, right? Although the lowest I've ever seen a measuring tape go is 1/32 of an inch, and they do talk about thousandths of inches in like very precise, like if you talk to mechanical people, they'll have measurements in like the thousandth of an inch and stuff like that, which is not precisely base 2, but you know, it's actually pretty close. 1024 is quite close to 1000, so you can get a reasonably close base 2 approximation, but I digress. So this has some interesting consequences, right? In particular, normally what we are interested in is the conversion of decimal fractional numbers into a binary fractional representation, right? So let's examine a fairly famous example, 0.1. We saw this example, you guys remember from the beginning of the course where I added up 0.1 10 times and it did not equal 1? We're about to revisit that and discover what the actual reason for that is in terms of underlying representations. So, let's see what we can do with 0.1. If we had 3 bits to represent 0.1, the closest we come is 001, which is 1/8, which is 1.25. This is not a terribly good approximation of 0.1. Adding 2 extra bits, the closest we can come is 0.00011. This is 1/16 plus 1/32, which is well, not approximately, it's equal to 0.09375, which is a closer approximation than 0.125, but is still quite some distance away from 0.1. Adding an additional 4 bits to our representation, we get 0.000110011. Adding all of this up together, we get 0.099609375, which is a reasonably close approximation of 0.1, but we are still not hitting 0.1 exactly. It turns out that in order to represent 0.1 inside of the binary system using binary numbers, you would require an infinite number of binary digits. There's a very specific and good reason for this. This is a rule of numbers. A number can be fractional, that is to say, it can have finite fractional representation. You can write a finite fraction to represent a number, but it might not be possible to represent that number with a finite number of digits in some kind of decimal representation, right? The most famous example of this is 1/3, right? The number 1/3, again, if you hit 1 divided by 3 into your calculator, you get 0.3333333. Everybody knows that that's not, everybody knows, I hope at this point, that the 3's are meant to continue on to infinity and we just round them off. That's okay. We round them off after, a certain number of, a certain amount of time, kind of you get the point level of understanding of the number, right? The actual mathematical reason that happens is that in order for you to be able to represent a number with finite precision inside of a number system, you have to be able to express it as some number over some power of the base of that system. Right? This is a rule of numbers. So, it turns out that if you take 1/3, there's nothing you can multiply, there's no whole number you can multiply both the top and the bottom of that fraction by to coerce the bottom to be some power of 10. Right? That's why 1/3 does not have finite representation under the decimal system. The same is true of binary arithmetic. So the number 0.1, which of course as a fraction would be 1/10, there's no number, no whole number you can multiply 1/10 by in order to coerce 10 to be some pure power of 2. It's not possible, right? So, many of the numbers which we know and love do not have finite representation under the binary system. 0.1 being one such example. I'm pretty sure 1/3 also doesn't work. Yeah, 1/3 won't work. Basically, if you can boil it down to a prime number, and that prime number is not, 2, then there you go. 1/7 also wouldn't work. So all right, so we need an infinite number of digits to represent these numbers. Can computers contain infinite numbers of digits? Not finite ones. You would have to build a computer the size of the universe, and you still wouldn't be there, right? And that just seems like a lot of work to go to represent 0.1, right? If we were going to build a computer the size of the universe, we would probably want to use it to do something cool, like a universe simulation, or something like that, We wouldn't use our universe computer just to represent a very, very, very accurate number. Especially when a fraction would do just as well. So, over the course of the development of computing as a science, very intelligent people from standards organizations have developed a particular representation which all computer systems use. This is known as floating point representation. Yes, fine, good. So, the floating point standard has been put together by both the IEEE and the IEC. I believe IEEE stands for International Electronics and Electrical Engineers, or something like that. I always forget what the acronym stands for. But the IEC is the International Electrotechnical Commission. Both of these are standards organizations that write very long documents that tell people how to design hardware, how to do lots of sort of common basic things that have produced the modern world, basically. Do not underestimate the power of standardized parts, right? Back in the Victorian days, when you put together a steam engine or a steam system, they actually cut the bolts to the screws each time. So each nut on a boiler would only fit with one screw on that boiler. That's how things were done prior to the existence of standardized parts. Obviously, since the development of standardized parts, things work much more easily. You can use the nuts on any bolt you might please. This is kind of a similar idea. Because all computing systems use a standardized representation of floating point math, and incidentally, this standard representation is baked into computers at the hardware level, right? Each computer system can communicate a floating point number to another computer system without it getting scrambled or garbled or start representing numbers that it's not intended to represent by the originating system, right? So, if not for the standardization of floating point math, you would not be able to communicate floating point numbers over the internet, for instance, right? Your thermostat would not be able to communicate with your furnace. All kinds of stuff like that. So standardization is extremely important. So under double precision floating point arithmetic, double precision floating point arithmetic uses 64 bits. Single precision is 32 bits. Use doubles, I'm pretty sure that Python is using doubles by default in the background, though in theory you never have to actually declare whether it's double or float. under double precision floating point arithmetic, you have 52 binary digits, right? These 52 digits those are the number of digits used to represent the fractional component, right? So 52 digits are permitted in this long chain of digits. Now that's pretty precise. We're only doing 9 here, and we've got, maybe approximately 3 digits of decimal precision. Using 52 binary digits, you get approximately 16 digits of decimal precision. Now, this is more precision, this is enough precision to accurately represent, the mass of electrons and electron charge and all of these very, very small, physics constants, which are among the smallest numbers which we know of, right? So this is generally considered good enough. So you might be asking yourself at this point, okay, so where are the rest of the bits going, right? So this is where we get into why floating point is called floating point. Floating point is actually a form of scientific notation which has been expressed in the binary system. So the rest of these bits, one is used to denote the sign of the number, right? So positive or negative, right? 1 bit for that. 0 is positive, 1 is negative. The rest of these are going into the fraction, the exponent, right? So we have some number represented by 52 bits multiplied by 2 to the power of some other number represented with the remaining 11. And of those remaining 11, that will be using 2's complement, I think, rather than sign magnitude notation, to the 2's complement that we talked last time in class, because that's expected to be an integer, right? We don't put floats nested in floats, that would be ridiculous. Good. If you're at all curious about what the precise representation of a number is inside of Python, it's actually possible to expose this using formatting. So if we format, incidentally, this format command is, once again, talking to the C standard libraries in the back end. So, I don't know, that kind of makes it too dark in here. There we go.
The camera
So,
does not want to focus on the code.
If we want to format a number like 0.1 using 60 decimal digits, this is how you do it. You'll notice
Oh gosh.
our representation of 0.1 continues on for about 15, 16 decimal digits, and then we just get random numbers, right? Essentially random numbers. If you were to actually do out all of the math here, you would find that this would be the sum of some number, some combination of, inverse powers of 2, right? But, it's, a lot of, 52 of these. We're not going to do that in class. You can just take my word for it. If you really want to do the math, do it for homework. But I imagine probably exactly and precisely 0 of you will do that. So, are there any questions about floating point arithmetic so far? Yes?
Well, do you really have floating point numbers when you have double? Isn't pretty much the same thing? But double is more precise?
Yeah, so floating, the question is why do we use doubles when we have floating points?
Yeah.
Is it?
Yeah, or
or vice versa?
Yeah.
Why do we pick one versus the other?
Yeah.
It depends on how much precision you want, how much memory you wish to occupy. In general, for people in this class, computer science students, you're not normally concerned with optimizing things at the level of individual bits. To you guys, the use of a long integer and a short integer doesn't normally matter. You usually just are concerned with integers themselves, period. Basically, if you want your program to take up less memory and you don't need the added precision, you can use float instead of double. If you don't know whether you need the precision or not, it's probably safer to use doubles rather than floats, which are smaller and more memory concise. You know, it depends on at what level you wish to optimize, right? Doubles are a pretty good general go-to case because they give you all the precision available. But, you know, keep in mind that these representations were developed at a time when the total amount of memory available in a supercomputer would have been, you know, some number of kilobytes, right? So at one point in history, memory was extremely expensive. These days, it's extremely cheap, so you don't really have to worry about crunching your doubles down to floats anymore the way you used to, unless, of course, you're in some very specific domains like hardware design. Does that make sense?
Yep.
Data types will no longer be this kind of, you know, touchy-feely, ephemeral subject once you get into C. If you don't understand data types when you're programming in C, you can't program in C. Sound good?
Yeah.
Any other questions? Okay. So, very good. So, we have this problem then. If our numbers are not being exactly represented, we can have a number of interesting effects with this. Now, the first interesting effect is that the equality comparison operation becomes unreliable. Equality comparison is like very exact equality. It works basically the exact same way for any type of data that uses the operation. Equality is one of those sort of immutable CPU operators, right? Equality means equality by the bit, right? In order for two variables or in order for two numbers in the computer to be the same number, according to equality comparison, they must have the precise same sequence of ones and zeros composing that number. Now, what happens with floating point numbers, this very small imperceptible error might not be so imperceptible after particularly repeated applications of other arithmetic operators. This is where the 0.1 added to itself 10 times does not equal 1 thing comes from. Because the number 1 does have finite representation under the floating point arithmetic model, right? Whereas any combination of 0.1s will not. Even if you construct something from these 0.1s that does have exact decimal or exact binary representation, the errors that are accumulated through the inexact representations will come out in the final number, or possibly not. It's actually very difficult to predict. So, not using equality on floating points it's an extremely tricky bug, because sometimes it will work, sometimes it will not work. It's safest to never rely on it working, right? Does that make sense? So you might be asking yourself, All right, so if we don't have the ability to, if we can't compare floating points being exactly equal to each other, how do we perform that kind of equality comparison? Because presumably we're not just, tying our hands behind our backs and never using equality for programming, right? An equivalent operation is to calculate the difference between the two numbers that you're trying to calculate the equality of, and checking to see if that difference is smaller than some small number. So in order to do that, you must take the absolute value of these two guys, in case that ends up negative, right? Because this single, like you could also test to see if it's, within negative and positive epsilon, but that's generally more CPU operations than doing it this way, and therefore slightly less efficient, although again, though inefficient, it will work perfectly well, right? So what you're doing is you're actually testing things within very tight ranges, right? So 0.1 plus 0.2 does not equal 0.3, right? However, if we say x is 0.1 plus 0.2 and y is 0.3, if we say the absolute value of x minus y is less than or equal to 0.001, that does come out true. So you're testing it within some particular degree of precision, yes?
Then normally what's gonna be the value of absolute?
Yeah, so it's selectable. You as the programmer have to come up with an epsilon that works. Generally speaking, things aren't going to be equal within, 1, 10, 100,000, 10,000, 100,000, like about a billion. If they're 1 billionth, if the difference between them is less than a billionth, then we can probably say that they are as similar to each other as we would expect anything that we are testing for equality to be, under reasonable definitions of how far apart numbers should be, right, to be considered the same number. Basically, they're close enough that you're not, you can say, well, these are approximately equal, right? It's an approximation. But then again, floating point itself is an approximation, so it is what it is. Does that make sense? This is a reliable method of testing equality. This will work every time. The equality comparison itself will not work every time. It is very, very, very difficult to predict when it will work and when it will fail. Make sense? Good. Moving right along. So, this is another, I'll run through this slide reasonably quickly because we've kind of already explained it. Important piece of nomenclature. The fractional component of the floating point number is known as the mantissa. You will likely hear that word in later courses, probably not until third year, but mantissa is the word. So, the 11 bits on the exponent in standard floating point representation gives you an exponent range from negative 1022 to 1023. Note the inequality of range, denoting that this is in fact being represented with 2's complement. This means that the largest positive number that can be represented is approximately 1.8 times 10 to the 308th power. You cannot represent numbers larger than this using standard floating point math. And the smallest possible positive number is 2.2 times 10 to the negative 308. right? So, in general, that is a very large number, right? This is a very small number, and it's kind of been designed so that in the entire course of human history, we've never needed to represent a number that large or that small, except for fun, right? Like, if you think about your typical engineering contexts, you know, this is like far, far, far greater than the number of atoms in the universe, right? And this is far, far, far smaller than the mass of any subatomic particle, right? So, you know, assuming you're talking about one of those subatomic particles that even has mass, I'm not a particle physicist. So, yeah. Question?
Isn't the smallest number of an 11-bit number negative 1024?
This is in decimal, base 10.
Oh.
Yeah, so if you take, yeah, and I don't know, isn't the negative one supposed to be like one more than the other one?
Yeah.
I'm pretty sure. That might be that might just be a mistake in the slides. 2's complement arithmetic in the exponent. However that comes out for 11 bits, that's what the range is. So we've examined the problem of equality not being a reliable outcome. So let's think about this number for a bit, right? 1.8 times 10 to the 308th power. What do you think happens in floating point arithmetic if we add 1 times 10 to the 0, shall we say, to this number? Keeping in mind that it's claiming to keep track of, you know, over 300 decimal digits here. Yes? It wouldn't be counted. It would fall off at the end of the universe. Absolutely. It turns out that you can actually, you can do this in Python relatively easily, actually. So if you have some big floating point number, as so, and you add 1 to it, there you go. 1 times 10 to the 16th power. Incidentally, this is fairly common notation inside of computer systems if you've never seen it before. E means times 10 to the. It's a very old notation. So here's the thing though, right? If we make this an integer rather than a float, we can see that the number, this 1 has not been lost, right? So large floating point numbers have a tendency to gobble up small numbers that they get associated with, whereas in integer arithmetic, you actually get the precise answer that you intended. Make sense? This might be, you know, you might be saying to yourself, okay, sure, but when am I ever using, you know, floating point numbers this large? As we're going to see at the end of the slides in this lecture, you can, during the course of calculations, have intermediate values which pop up to this things on this order, right? So if you think about equations which have a lot of multiplication and subsequent division in them, right? If you were calculating, you know, x to the power of 6 divided by x minus 7 to the power of 5, and x was, you know, reasonably small actually, like maybe 1,000, you might get into situations where the intermediate values of x will blow up to a size where this type of arithmetic, this gobbling effect, will in fact throw your answer off. Make sense? Question?
If you use formats on the 1e plus 16, would it show the 1 at the end or no?
Excellent question. Let's format that and check out the number. Don't believe me, eh? That's okay. You should never trust your professors. Question everything they tell you.
No.
So this is the same number with 60 decimal places shown. And you can see, at no point is that one represented. Make sense? I'm serious about that, though. You should always, like, the professor, if they're worth their salt, should be, and I know I'm gonna get burned by this myself, but a professor worth their salt should always be able to explain to you why the thing they're saying is true. All right? You should, like, you people are scientists. You shouldn't be taking things on faith. All right? That's a different department. Social sciences. Just kidding. Yes?
Just out of curiosity, how many bits do the calculators that we use?
Oh, that's an excellent question. So how many bits do the calculators that you guys use? I would say it might depend on the calculator. The thing about these types of commercial electronics is that the chips that go into the calculator itself will not have been designed by the manufacturer of the calculator. These chips will be designed, you know, by people at the Taiwan Semiconductor Company, or, you know, that's like at a different point in the chain. Like, basically, it doesn't really matter what model calculator you're using, they're all using the same chips. You know, it's like, I think it was in the movie, like Armageddon or something. The one where they have to go up and blow up the meteor. It's like, Russian parts, American parts, all made in Taiwan, you know? The parts that are being used in your calculator will be compliant with the IEEE specification unless there's a very good reason for them not to be, right? And there's no good reason for them not to be. So while this is kind of outside of my particular domain of knowledge, I would be very surprised if your calculators didn't use standard double precision floating point arithmetic. Even though technically they only represent things to like 8 or 9 decimal places on the display, so probably single precision would do, but they probably use double anyway. Particularly like the graphing calculators, like the McMaster standard calculator is actually, it does quite a lot. You know, it can calculate matrix determinants.
Yeah.
That's very cool, right?
Oh, this is.
Anyway.
Yeah.
Success in this program will be slightly dependent on your ability to use your calculator. It is your tool. Learn how to use it as the master carpenter knows how to use his hammer. But anyway, any other questions?
You need to give it a point. I think you can solve cube
Okay.
functions too and things.
Yes, good. So, let's discuss some alternatives. We have noted that there are some problems with floating point arithmetic. How would we represent numbers in such a manner as to get around these problems? In general, in Python, we have two approaches, the decimal library and the fraction library. In other languages like C, you just have to deal with it. And frankly, in Python, it would probably be a good idea to learn how to deal with it. A, that makes your skills transferable to other languages, and B, these are compromises at best. They will work, but at what cost? Answer, time and memory. So, like the decimal library, for example, is 3 times slower than floating point arithmetic on average. So, arithmetic with the Python decimal library will produce the same errors as calculations by hand. Asterisk in theory, I've seen it not do that. By default, 28 fractional digits are kept. The precision can be changed. So if you want more than 28 fractional digits, you can specify that because it's basically doing a bunch of memory work at the back end to, produce a different representation of the number that is not susceptible to the same problems that we have in floating point arithmetic. Equality comparisons work, for example. Yes?
So calculations by hand meaning long precision working it out slower.
Yes. Yeah. Precisely. So there is one problem with the decimal library, though. If float go in, float come out, right? This is, okay. This, I can't believe it's taken us this far, but this is the universal law of computing, right? You must live and die by this, the one natural law of computing. Garbage in, garbage out. If you put a floating point number into the decimal library to initialize a decimal number, it will read it with all of the floating point imprecision that is native to the floating point representation, and therefore you're not actually gaining anything. You might as well just be using floats, right? The way to do it, because this is Python, is to represent the number as a string. So if you express the literal as a string, it will read it as a string. It's not a float, and therefore it will work correctly. The alternative is to feed it integers and perform whatever arithmetic is necessary to derive the decimal number that you wish to represent. Float go in, float come out. Okay? I will show this. I will demonstrate. So, from decimal import decimal, did I get that right? One of them capitalized, I'm pretty sure. Yeah, okay. Decimal as D. D just lets you rename it so that it's not as long to type. So if we have D at 1 divided by D at 3, again, not capable of representation in finite decimal arithmetic because it's, we would need ternary arithmetic. But if you have 10, there we go. However, if you simply represent 0.1, you are no better off than you were before. Make sense? Good, good?
Yeah, good.
Good. Incidentally, it is possible to convert to a string and then to a decimal in the decimal library. So, if you'll notice, if we have some number x, which is fine, if we format that, add format x, give it, say, 6 decimal digits of precision, notice that the output here is a string, right? So, you can then chunk that into the decimal library, and that's one way that you can take a float, convert it to the decimal library. You just have to pass it through string conversion first. Incidentally, if you have a number, the string converter library, I believe, also does. Nope, it'll do quite a few digits. So if you want, this is like a sneaky way of rounding without using the round operator. Okay. By the way, on the subject of the round operator, given that floating point imprecision is embedded in the very hardware of your computing device, will the round function remove it?
No.
No. You cannot overcome the binary representation of numbers using any function in a computer, right? Even though round says it rounds a number, what does it round it to? Another floating point number that also has floating point precision problems, right? Make sense? Good. So there's no sneaky things. There's no trick that's going to move that rock. You just have to face it head on. So, good. So why do we not use it? Why do we not use decimal for everything? Question?
Is this like the problem for like every language, or is it for Python specifically?
This is, so the question is this a problem for every language, or is this just a Python problem? It is a problem for every programming language that operates on a computer. If you had a programming language that you were doing by hand, it would not be subject to floating point error. But any programming language which is fundamentally implemented on a computer system has this problem. So yes, effectively all programming languages. Although once you start getting into third year, you sort of get into the realm of like the idea of esoteric languages that are just on paper, which are used as the mathematical bases for other languages, right? So like you have to, like, there is a decoupling of programming languages from hardware that does occur when you get high up enough in the math, right? They're not the same concept, an implemented language on a computer and the idea of a programming language, but for all intents and purposes, for the purpose of becoming just a regular normie programmer and not a super math whiz, which I'm sure is the intention of most people in this program, actually. Effectively, all programming languages have this problem. But I'm not sure, like, I think a lot of people were lied to when they came into this program. They imagined that this was like the software engineering program, and no, this program focuses more on math. It's just a fact. That is the distinction between software engineering and computer science at this university, regardless as to whether other programs do or do not recognize that distinction. But anyway, I'm not quite done yet. We still got 2 minutes. I just want to briefly talk about the fraction library. The fraction library is another alternative to doing the same type of thing. Rather than representing number as one string, which is, some number of decimal places, under fractional representation, we represent things the same way that we represent fractions every other way, using the ratio of 2 numbers. Right? So under the hood, fractional representations are a collection of 2 integers which are multiplied and divided together in the particular fashion that produces the fractional arithmetic that you learned in elementary school. Hopefully. I sometimes wonder whether people even study fractions in elementary school anymore. So, in general, floating point is to be avoided whenever possible. One way of avoiding floating point is to use equivalent integer representations. If you're representing dollars with cents, just do everything in cents and save yourself the decimal point. Your math will be more exact. Same thing with meters and millimeters, right? That's what, like, integer arithmetic is precise, so you can avoid floating point problems that way. Anyway, class is over. Thank you very much, folks.
How do you tell me? I don't know. Which you? I think you just push the button. Yeah.